All right, kids, time to do double integrals over a general region. And this is going to take us a couple of sessions. So a general region, which remember from our previous lesson, this is different from when we just had a rectangular region. Right? And a rectangular region in our XY plane just meant that we had very defined boundaries, right? We had some nice, very horizontal, vertical boundaries, right? So I want to recall back, of course, to Calc 1, Calc BC, when I asked you to find the area between two curves, right? So if I gave you the curves 2x and x squared and asked you to find the area between, you were expected to draw it, and then you were expected to identify the points of intersection, right? And the area was top minus bottom, right? But when you did top minus bottom, it was because you were drawing little teeny rectangles, right? Little strips that were vertical. So you use the x coordinates from intersection and said, okay, we're going to integrate from 0 to 2, creating a bunch of rectangles where the top is created by 2x and the bottom is by x squared. So we were integrating everything with respect to x, which means this was a function in terms of x, this was a function in terms of x, and these were x numbers. But then I said, oh, by the by, you could find the area is the area, right? So you could, if you wanted to, kind of switch your frame of reference and say, hey, I think I want to draw a horizontal strip, right? Drew a really, really thin horizontal rectangle. And with a horizontal strip, then you were doing right, the furthest to the right minus the left function, right? Right, get it? So you were integrating with y, right? Because you were moving along, clicking and dragging that in the y direction. So you use the y coordinates from the point of intersection. You had to tell me you were integrating, right? That the strips were pointing at the y-axis and that was going to move up and down. You were going to change delta y, right? Was the width of your rectangle. But then you had to write the equation in terms of y, right? Everything had to match. Delta y, 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 y numbers, right? Now let's go to multivariable. So what if I want to find the volume under a surface? So again, I'm in Z space and this surface is up in Z space but my XY plane is bounded by this non-rectangular region we'll call D. I don't know why they call it D. So this is not a rectangular region. The region is the one that I just gave you in the XY plane. So here's what it looks like if I put the XY plane down on the floor, right? Can you see my Y is equal to 2x? And my y is equal to x squared, right? And those are my xy points of intersection. Here's what that looks like in 3D, right? There's my non-rectangular region down in the xy plane. This view is kind of wonky because I didn't go high enough for you to see the point there, but you get the idea. And here's the GeoGebra. If you want to look at it and mess around with that region, here's the GeoGebra link to it. But what I need to do is I need to take this region, this D, I want to take it off of here, identify the region in the XY plane. Then I want to rewrite delta area in terms of either dx dy or dy dx. And I want to put limits here. When we had a rectangular region, those limits were all constants. But now we are going to have a different situation. We are going to imagine that we have either the scenario in the XY plane. So now I'm just drawing the XY plane. Where we kind of have these vertical bounds and the Y values vary. They're curved, right? Whatever they are. So this is Y equals a function in terms of X. And we are going to draw, just like we did in Calc 1, we are going to draw vertical strips in there, down on our domain. Or we have this scenario where we kind of have horizontal bounds and we have some kind of curve on the right and left end where X is equal to Y stuff. Okay, so that's where I have to kind of like, this is going to be type 1, this is going to be type 2. And that decision is going to make this decision. Okay? And it depends upon the situation, right? I don't really go into it knowing what I'm going to do. I have to draw and think it first. So let's see what we're going to do with this. So again, first I'm going to determine what strips you're going to draw through my region in the XY plane. And that step means draw your domain first. There's my domain. If I want to draw vertical strips through there, and here's just like when I was in Calc 1, here's one of the things I think. I kind of imagine, right? You're the click and drag generation. Imagine I can put my cursor on this vertical strip and drag it left and right through the domain, right? Through the X's, right? Changing the X's. Does the top of my boundary ever go off of Y equals 2X? No. Does the bottom of my strip ever go off of the bottom boundary, Y is equal to X squared? No. Since I can drag my strip, I just chose vertical first, and I drug it through. And when I drug it through, the top boundary and the bottom boundary stayed the same. That tells me I can keep going. So if you have vertical strips, the inside integral is dy. So remember I told you that the strip determines whether you're going to have dy dx or dx dy. So type 1, you're going to have dy first, then dx. And if your inside integral is dy, the inside limits are your functions with x in them. Y equals 2x. Right? I have functions with x in them. Oops, I don't know why I made that subscript there. Instead of a superscript, right? So check. Next, The outside integral then is going to be dx, because I'm going to integrate. I'm going to use iterated integrals, and I'm going to integrate the inside first, and I'm going to integrate it with respect to y, but I'm going to replace then the y's with x functions. Then I'm going to go to my outside integral, which is dx, and my outside bounds are the constants. Now, where did I get those constants? From your points of intersection. Okay, and we already know that's 0, 0, and 2, 4, so we're going to be using 0 and 2. So here's what that looks like. I split up my double integrals. I don't have this d anymore. Because I drew a vertical strip, I did dy dx, right? dy was first. That means my inside limits are functions in terms of x. So I like to think of it like this. This is y equals 2x and y equals x squared. And then these are the constants that come from the points of intersection. And they are x numbers. So x matches the outside variable, y matches the inside variable, right? So my inside limits are x functions. And I should say functions in terms of x might be more appropriate. The outside integral is dx, check. And the outside bounds are x numbers that came from my points of intersection. Now I'm going to do my integrals. I'm going to look just here and integrate this dy, which means I think of x squared as a constant. So integrating this, just this inside part, the antiderivative of a constant is what? That's going to be y, isn't it? Right? It's not 0. So integrating just the inside part, this is a constant, so it's going to be x squared y plus y cubed over 3. Right? Think of this as having a y to the 0. And I am going to evaluate that at y equals x squared and y equals 2x. So replace the y's. Using the second fundamental theorem, replacing the y with my x functions, or my functions in terms of x. So what do I have? I have x squared y plus y cubed over 3. Second fundamental theorem minus what? X squared times x squared plus x squared cubed over 3. I wish I could tell you this is nice, but it's really not. So what do I have here? 2x cubed, right? Plus 8x cubed over 3 minus x to the 4th plus x to the 6th over 3. All of that is integrating here. I now need to replace that gray box, and I'm going to integrate the outside. But notice it's all now in terms of x. So what do I have here? Is that a plus? Yeah. So what is that? 6 plus 8 is 14. Dx. And now I'm just down to Calc 1, integrating an x function, right? Dx, everything is in terms of dx, and these numbers are x numbers. Now, the nice thing is when I put in 0, everything's going to go away. So I just really have to do, what is that, 7/6 times 2 to the 4th minus 2 to the 5th over 5 plus 2 to the 7th over 21, whatever that is. Right, I get out my calculator and I plug and chug, right? That was step 5. So if I wanted to do the same thing, I could do, in this case, because as I showed with the Calc 1 diagram, I could have just as easily done this the other way, right? Because my figure, right, if I integrated dy, my right bound never changes. As I clicked and dragged up through here, my right bound never changed, my left bound never changed. So I could have done this the opposite way. Type 2 with horizontal strips. Horizontal strips means your inside integral is dy. The inside limits are y functions. So do you see what I did here? I had to take y is equal to x squared and y is equal to 2x and get each one of them in terms of y, right? Because I'm going to integrate dx, which means I'm going to treat y squared like a constant. But then I'm going to replace the y stuff from integration by the second fundamental theorem with x stuff. Then I'll do this one. Then I will just be integrating a bunch of y terms, dy, with the outside bounds are y numbers from, again, your points of intersection. Okay, I leave that one for you to do. Oh, I forgot that I drew that. All right, let's do this one. So find the volume under a surface. Here's my surface, x plus 2y, bounded by a non-rectangular region, D. So my job is to take this double integral, get rid of D, get rid of dA. So first I want to draw. Just draw in the xy plane. You don't have to draw, no one's asking you to draw this surface. So in the xy plane, what do I have? Right, 2x squared kind of looks like this. And 1 plus x squared looks like that. So the region that is bounded between them is right here. So ask yourself a question. Should you draw horizontal or vertical strips through there? So hopefully you can see that if you draw horizontal strips, right, your left boundary is 2x squared and your right is 1 plus x squared here, but for the top of the region, but at the bottom of the region, my right and left are both defined by 2x squared. So hopefully You think vertical, because when a vertical strip, notice when I draw a vertical strip, no matter where I draw a vertical strip, my top boundary and my bottom boundary are the same. Now, sometimes, right, it could be so that no matter which way you look at it, you've got a boundary change, which just means, just like in Calc 1, you have to do multiple integrals, right? You just have to break them up. Every time your boundary changes, you have to create a different integral. But if you can keep your boundaries the same, it reduces your workload. So how should I write this? Right, what do I do here? I want to replace, right? I want to replace, this is my D. I've decided I'm going to do vertical strips. So the next thing I do is transform this. I transform dA into what? dy goes first, dx goes second. And if dx goes second, that means your constants go on the outside. Set up your double integral, find your constants. Right, so dx, what are my constants? My constants come from here. Where does 2x squared meet 1 plus x squared? And sometimes I do like to remind myself, right, what my variables are. Do your equations, right? What are my equations? So since dy is in the inside, whoops, I meant to put these over here. X is equal to -1, x is equal to 1. dy means over here goes y equals x stuff. So what's my bottom? What's my top? Oops, sorry, I did that backwards, didn't I? The top is 1 plus x squared. Right, the top, y equals 1 plus x squared. All right, so now I go back to my algorithm. What was I supposed to do, right? Integrate. So remember, there's actually a y. I'm integrating with respect to y, so think of a y0 there. So I end up with xy plus y squared over 2, which means that 2 is going to go away. And I'm going to evaluate that at which means I'm going to replace each one of those y's with x stuff. Now you can see that these get pretty nasty pretty quickly, which means, right, your algebra does have to be good. I'll just tell you what I got here. Because remember, this is just step 1. You are just doing the beginning. Don't forget that you have your second piece. You are going to end up integrating from -1 to 1 after I expand and do all that nonsense in there. But you can just trust me that you would get negative. Hope I did my algebra right. dx, but now you're down to a Calc 1 problem, right? So you're down to a Calc 1 problem. You're going to integrate piece by piece by piece here. You're going to put in 1, then you're going to subtract, putting in, when you put in -1. When I did this, I ended up with 32 over 15. And I do have to say that I put a lot of this into my calculator and then I math fractioned it. Okay. I don't really care at this point, your straight up calculations. I mostly care, can you set it up correctly? Can you make good decisions about how to set it up? And, maybe can you get through, can you get down to the Calc 1 part, maybe? So here's something that you might be asked to do. Instead of actually finding the volume, maybe I just ask you to set up the problem. Okay, so I'm not even asking you to do any integration. I just want you to set it up. So if I wanted you to set this problem up, right, I want you to take over the non-rectangular region, draw it. And I wrote it out like this because sometimes your book likes to write it like this, which I think is kind of silly, but whatever, right? Can you draw that in the XY plane? Well, if x is going from 0 to pi, and y is sine x, y is less than or equal to sine x, right? So isn't it just that? That's a terrible drawing, by the way. So what am I going to do from here? I am just going to, right, you could do either one. Why not do vertical? And then you're going to replace this D. Right, I only have an X in here. I don't know why I left such an awkward space. But since X is here, I already had constants, right? 0 to pi, since Y is here, I need to make sure I have an equation that has X stuff. Well, there you go. Right, this actually wouldn't be that, oh, sorry. Y is equal to 0, Y is equal to sine X. Sorry, I was pointing at the wrong place. Right? That actually wouldn't be devastating to do. What about the next one? Okay, a little bit different. My surface, right? Don't worry about picturing the surface. You need to picture this. What's going on here? Right, when I draw this, negative x plus 1, should have drawn this first, y equals 3. And x plus 1, right? So the region I'm interested in is here. That's my D. So what kind of strips would you draw here? Right? If you draw vertical strips, your top boundary stays the same, but does your bottom? No. So I think I will not do dx, right? I think I will not do vertical. So because when I do my horizontal strip, look, no matter where I click and drag that strip, right? My right and my left boundary stay the same. So what does that mean I need to do? keep my integrand the way it is. But this time, since I am got horizontal strips, dx goes first, dy goes last, which means y constants have to be there. Well, what is the y constantly? Right? 3 up here. And where did it start? Right? What's your lowest y? 1, right? Then how about here? Since this is dx, these functions have to be x equals. So who is my right function? This is my right function. This is my left function. So this is x equals y minus 1. And my left function good? All right, last one. So one of the reasons I chose this is because most of the examples that I get, well, I guess this one too, right? Like sometimes you can make the mistake that if the equations are given to you as y equals, that you should definitely be doing dy dx instead of dx dy. But I want to make sure that you understand it's the drawing. It's the drawing that makes this difference, right? So I'm going to draw up here. Now, maybe you're not sure what this looks like. Well, I hope you know what that looks like. Ah, that's terrible.
All right.
So about y equals x minus 1. That's not too bad, right? Maybe you don't know what this looks like. Maybe you do. But think of it. What would it be if I had, right? If you had x is equal, the x is equal to y squared stuff. If I had x by itself, maybe you'd recognize that, right? It's a sideways parabola, right? It opens to the right because the y squared is the coefficient from there is positive. And what if I put 0 in here for y? What would x be? 6 divided by 2 or 3. So it kind of looks like this. So the region that I'm interested in, the non-rectangular region, is right here. That's my D. So think about the strips. What kind of strips would I be drawing through here? Do I want to do vertical strips? I don't think so, right? I have a boundary change. But what if you draw horizontal strips? No matter where you go, the left bound is always that parabola, and the right bound is always the line. So our job is to replace the D, keep the xy the same, and replace the delta A. So since we decided we were going to do horizontal strips, we're going to do dx dy, which means your constants go there. And where do your constants come from again? Ah, points of intersection. This is a little harrowing, right? This one's not quite as obvious as this one was here. So what do I need to do? I need to find the right points of intersection. Y squared is equal to 2x minus 6. right? Y plus 1, if I just add 1 to both sides, that's going to be 2y plus 2. Oops, sorry, this is supposed to be a plus 6. I'm sorry. I was going for my notes, which is why that's a negative 3, not a positive 3. Sorry. So plus 6. So I get y squared minus 2y. When I move all this over, that's a plus 2 and a plus 6, which is a plus 8. Move it over. Minus 8 equals 0. Factor. So these points of intersection are something, comma, 4 and something, comma, negative 2. And those, remember, are y numbers. So this is dx, so what do I need to go here? I need these functions to be in terms of. Right? X equals. So who is my right? My right comes from here. So I've already gotten that by itself. X by itself, y plus 1. And then how about this one? Can you get x by itself, right? It's going to be y squared minus 6 all divided by 2. So that's 1/2 x squared minus 3. All right. So again, for this objective, really the setup is the most important piece. And yes, you will have to evaluate some, but and it can get harrowing. But if you can get the setup right, you can get a lot of follow-through points, even if you do the integration wrong. All right, I will see you on Tuesday.